Welcome to the Explainer. Today, we're diving into how mathematical modeling takes abstract formulas and, well, actually uses them to solve incredibly practical, real-world physical design challenges. I'm absolutely thrilled to guide you through this today because we're going to look at math not just as numbers on a page, but as the ultimate tool for creation and efficiency. Let's get right into it.
Okay, so think about this. How exactly do we find the absolute best possible solution to a physical problem without wasting a ton of time and resources on trial and error? I mean, if you're a manufacturer, every extra square centimeter of cardboard or metal, that costs you money. You literally can't afford to just guess the right dimensions. You need a rock-solid method to guarantee you're making the most efficient shape possible. And that is exactly what we call mathematical optimization. Here's a quick look at our agenda for today. We'll be hitting 1. The art of modeling, 2. The tennis ball problem, 3. Modeling metal trays, 4. Finding maximum volume, and finally 5. ICT spreadsheet investigations.
Section 1, the art of modeling, and Section 2, the tennis ball problem. Let's jump right in.
All right, imagine this. A manufacturer needs to pack 12 tennis balls, and each one has a radius of exactly 3.3 centimeters. They need to fit them into a cuboidal cardboard box with a lid. Now, the fundamental constraint here is the material, the cardboard itself. The ultimate goal, to use the absolute bare minimum amount of cardboard possible while still perfectly fitting all 12 of those balls. It sounds simple, right? But the spatial geometry here is actually a brilliant puzzle. So, the logical approach here is to sketch out the different possible 3D arrangements, calculate the exact surface area for every single one of them, and then pinpoint the most economical design. This right here perfectly illustrates the core of mathematical modeling. You don't just jump at the very first idea. You systematically outline your options, you evaluate the variables, crunch the numbers, and let the actual data dictate the winning design. Now, this fundamental question of visualizing shapes to find the cheapest packaging, that's the starting point of mathematical optimization. Just think about it. You could stack all 12 balls in a single, super long tube, like a 1x12 arrangement. Or you could create a flatter box, maybe a 3x4 grid. Which one actually has the smaller surface area? Visualizing these permutations really forces us to rely on geometric formulas to find the real truth, rather than just trusting our gut instinct. Moving right along to Section 3, Modeling Metal Trays. We're starting with a completely flat rectangular sheet of metal measuring exactly 30 by 40 centimeters. Picture it lying perfectly flat on a workbench. Right now, it holds 0 volume. It's literally just a two-dimensional plane of potential. Our job is to transform this 2D sheet into a 3D container that can hold the absolute maximum possible amount of material. Okay, so by cutting squares of equal size out of all 4 corners and folding those sides up, we create a 3D tray. But here's the catch. The dimensions of that tray completely depend on the size of the cut we just made. If you cut a tiny square, you end up with a tray that has a massive base but incredibly shallow walls. If you cut a massive square, you get a tiny base with really high walls. Finding that perfect sweet spot is the whole point of this investigation. Think about how drastically things like the length, width, height, and overall volume change if we cut out a 1 centimeter squared compared to, say, a 2 centimeter square. With a 1 centimeter cut, your height is just 1 centimeter, your width drops to 28, and your length is 38. If you calculate that volume and then compare it to a 2 centimeter cut, well, your height doubles, but your base area shrinks significantly. The volume doesn't just change in a straight line, it shifts in some pretty complex ways. But before we even try to calculate the best tray, we have to determine the domain. Basically, what is the physical maximum size of X we can cut before the metal sheet essentially disappears? If the shorter side of our metal sheet is 30 centimeters, cutting squares from both corners means we're taking away 2x from that side. Logically, 2x simply cannot be larger than 30, which means x absolutely must be less than 15. This step grounds our entire mathematical model in actual physical reality. Section 4, Finding Maximum Volume. Let's see how this all comes together. This brings us to the really brilliant part, where we turn a physical object into pure mathematical code. This jumble of numbers and letters, a polynomial equation, is actually the exact DNA representing the volume of our metal tray based on the size of that corner cut. It comes from multiplying the new length, which is 40 minus 2x, by the new width, 30 minus 2x, by the height, which is x. When you expand all that algebra out, you get v equals 4x cubed minus 140x squared plus 1200x. It's honestly beautiful. We've completely captured a physical box in a single line of algebra.
Now, by plugging this formula into a graphic display calculator, specifically for the valid domain of x that we established earlier between 0 and 15, we can literally watch the potential volume rise and fall visually. You'll see the curves start at 0 volume, surge up to a distinct peak as the tray gets deeper, and then fall right back down towards 0 as the base gets way too narrow. Finding the highest peak on that specific curve tells the manufacturer the exact maximum volume down to 1 decimal place, completely eliminating the need for any physical trial and error. You don't have to ruin dozens of perfectly good metal sheets trying to find the perfect cut. You just find the local maximum on your graphed function. It's a total game changer that saves time, money, and materials. And finally, Section 5, ICT Spreadsheet Investigations. Let's take it up a notch. For this final investigation, let's look at how information and communication technology, ICT, handles some really complex 3D modeling. If you take a 10-centimeter radius circle, cut out a wedge or a sector, and roll up the remaining paper, you get a cone. But figuring out which cut gives you the biggest possible cone, that requires some seriously heavy calculation. As you change the angle of the sector you're cutting away, you are simultaneously changing both the base radius and the vertical height of your resulting cone. Doing the math for every single possible angle by hand would be incredibly tedious. Now, what's super interesting here is how a spreadsheet completely automates this process. We simply enter the angle of the sector, which we call theta. From there, we just punch in the formulas to instantly calculate the sector arc length, the base circumference, the base radius, the vertical height, and finally, the volume itself. We can set up the spreadsheet to calculate this for every single angle, from 5 degrees all the way up to 355 degrees. What would take a human literally days to calculate, a spreadsheet knocks out in milliseconds. Once the spreadsheet crunches all that raw data, plotting a graph of the cone's volume against the increasing angle theta beautifully reveals the optimal manufacturing design. You can visually track exactly how the volume surges and then slowly drops off as the cone gets too narrow and tall. The sheer power of ICT allows us to model a massive data set effortlessly to pinpoint the absolute perfect, optimal design. So here's the absolutely crucial point. Whether you're folding cardboard for tennis balls, cutting sheet metal for trays, or shaping paper into cones, mathematical modeling is the ultimate tool for optimization. It totally bridges the gap between abstract numbers and tangible physical engineering. It allows us to push boundaries and achieve absolute peak efficiency. I want to leave you with this final thought. Look at the objects and the packaging around you right now and ask yourself, what invisible mathematical formula was used to engineer its perfectly optimized shape? From the soda can sitting on your desk to the shipping box waiting at your door, mathematical modeling is quietly shaping our entire physical world. Thank you so much for joining me on this explainer. Keep questioning, keep modeling, and I'll catch you next time.